MAT 1122 Differential Equations 1 Lesson 1 Introduction and Definitions Elimination Graphical Interpretation. So equations such as d squared y over dx squared equals minus p squared y, and these types of equations we called differential equations because this is involved with the differential coefficients. So you know that if we consider these two, right, 2 3 minus 10, these are the coefficients. These are coefficients, and like this d squared d cube by dx cube and d squared y over dx squared dy by dx, these are differential coefficients. Right, so the equation involving the differential coefficients are called differential equations. Here you can see that there are differential coefficients, in here there are differential coefficients, in here also differential coefficients, and here also you can see the differential coefficients. So these types of equations are we called differential equations, right. (1.2) Differential equations which involve only one independent variable like 1, 2, 3, 4 are called ordinary differential equations. Here you can see there is only one differential, only one independent variable. So you can see here x is independent variable, here also x, here also x, right. So in not in equations 1, 2, 3, 4, x is the independent variable and y is the dependent variable. If it is included only one independent variable, it calls ordinary differential equations. These all equations are ordinary differential equations, right. An equation like 1 which involves a second differential coefficients but none of higher order is said to be of the second order, right. So order of the differential equation means right, if you consider this one, you can see this is d squared y over dx squared. So here there is a squared, so this is second order differential equation, right. Equation like one which shows the second differential coefficient. Here second differential coefficient is there, so this is second order differential coefficient. So if we consider this equation, you can see 2 times d cube y over dx cube, right. So you can see here there is a cube, it means power 3. It means this differential equation is third order, right. That is called order of the differential equation. If we consider this one, this is a second order equation and this is the first order differential equations, but you can take the highest derivative of the differential coefficient. So here highest derivative is 3, the 3y, and here dx, d 3y over dx 3, it means this is a third order differential equation, right. 3 is also in second order, 4 is the first order, and 2 is in the second order, right. The degree of an equation is the degree of the highest differential coefficient when the equation has been made rational and integral far as the differential coefficient concerned. So then now we find the order. Then next is we have to consider what is degree. Degree means if we arrange the differential equation in rational and integral, then we have to take the power of the highest derivative, then you can find the degree of the differential equations. I explained this using an example, right? So see, if we take dy by dx equals 3, right? So here power is 1, this means this order and degree, right? So if you consider this one, this is dy by dx, it means here 1, and this is first order differential equations. And power of this one, if we take the power, that is also 1, right? It means degree is also 1. If we consider d squared y over dx squared equals 0, so what is the in here that differential, if we consider the differential coefficient, there is 2, it means that is second order differential equations. And power of the highest derivative, that is 1, no, then degree is 1, right? So if we consider d cube y over dx cube equals 0, that is also differential equation. If we consider the highest derivative, that is third, then it means order is 3 and degree, then power of the highest derivative is here also 1, then degree is 1. Now we consider this equation, d squared y over dx squared plus 3 dy by dx equals 0. So if we consider this, this is second order, because you can see here order of the highest derivative, that is 2, so that 1, and power is 1, then degree again 1, because here power is 1, right? We are taking power of the highest derivative, it is equals to 1, then degree is equals to 1. Right, now consider this one, d squared y over dx squared to the power 3 minus dy by dx equals 0. So what is the order? Order is here, that is 2, second order, and degree means power of the highest derivative, that's highest derivative is d squared y over dx squared, then power is 3, so degree equals 3, right? Right, if we consider another one like this, d squared y over dx squared to the power half minus dy by dx equals 0. In this the questions like this form, what you have to do, first you have to remove this half. For to do this, what you have to do is, we can rearrange the equation equals dy by dx, then we can power both sides, then here creating d squared y over dx squared, and we have to take power of this side also, then dy by dx squared over 2, right? So if we consider this, what is the highest derivative? Second order, then order is 2, right? Order is 2. Degree, here you can see there is a square, and if we consider this one, there is a 1. So but this is not in second degree. Why is that? When we taking the degree, we are considering the power of the highest derivative. Highest derivative is not here d squared by over dx, dy by dx, not the highest derivative. Highest derivative is d squared by over dx squared, then here degree is also 1, right? I think now you have understand how you can find the degree and the order, right? Now consider this one, an equation like 1, so we can discussed, then thus equation 1 2 3 4 are the first degree. Yes, you can see highest power of here 1, here d squared, here highest power is 1, and 4 highest power is 1, but 3 we have to rearrange 3 to find degree, right? So first you have to, what you have to do is you have to take the power of this, because they are 2 over 3 is there, no? So what you can do is, you can power both sides, then what 1 plus 2 dx dy by dx to the power 2. If you power this, here creating power 3, and here 9 d squared by over dx squared to the power 2, right? So if we consider this, what is degree is power of the highest derivative. This is second order equals 2, and degree equals again here there is 3, but we are taking power of the highest derivative, that is as degree, that is also 2, right? So here then it is mentioned there, note 3 must be squared to rationalize it. So we squared and we can rationalize this. When you see that of the second degree as occurs squared, and then that is, then we see that is second degree. I show you how we can take that as a degree 2, right? Formation by a differential equations by elimination, right? The problem of elimination will now be considered, chiefly because it is gives us an idea as to what kind of solution a differential equations may have. We shall give some examples of elimination of arbitrary constant by formation of ordinary differential equations, right? We can see example how we can eliminate coefficients and forming a differential equation, right? So here consider the differential equation x equals a cos pt minus alpha, the equation of simple harmonic motion. Let us eliminate arbitrary constant alpha, a and alpha, right? So we can take, given equation is x equals a cos pt minus alpha, where a and alpha are arbitrary constants, right? They are arbitrary constant. So we can write, we can first we can differentiate with respect to t, right? So because here independent variable is t, so then we can create dx over dt equals, a is a constant, a derivative of the cos is minus sin pt minus alpha times, if we derivative pt, that is p, right? So we can create minus ap sin pt minus alpha, right? We can differentiate again, because there is again p is there, p and a and p is there. Differentiate again with respect to t. Then here you can take d squared x over dt squared equals minus ap, because that is constant, sin alpha, if we consider, that is cos sin alpha, if we derivate, that is cos pt minus alpha times pt, it comes p. Then d squared x over dt squared, we can take minus p squared times, I am write this a cos pt minus alpha, right? A cos pt minus alpha, that is x. So we can write d squared x over dt squared equals minus p squared x, right? So now we eliminate the arbitrary constants, right? Yes, that's how we take this answer, right? If we eliminate this a and b, so we can take thus the differential equations, and d squared x over dt squared minus p squared x is the result required, an equation of the second order whose interpretation that the acceleration varies as the distance from origin. Right, then the next question is eliminate free from the last result. So then now we have, right, now we eliminate that's correct. We have the arbitrary constant are given p, a and alpha. Then next, given that differential, we have to eliminate p from the last result. Okay, so we will go to the last result again. Right, this is our result, so we have to eliminate p now. Right, so we can differentiate again with respect to t. Then it's come d squared x over dt squared equals minus p squared dx over dt. Right, here we can here minus p squared is there, minus p squared is, I am taking this as first equation and this as the second equation. Then 1 divided by 2 implies d squared x over dt squared divided by d squared x over dt squared equals, if you divide this 2, minus p squared cancel, x equals d x over dx by dt. Right, so here d cube, no, second equation. Then x times d cube x over dt cube equals d squared x over dt squared times x. Sorry, not x. If you cross multiply, it is come for here, no, it's go times dx by dt. Right, so this is, I think, now we eliminate the, yes, so then this is our equation that is in third order, so we can remove p also. Right, to eliminate n arbitrary constant requires integral a differential equation of the order. Suppose we want an equation containing n arbitrary constant. If we differentiate n time, we will obtain n plus 1 equation altogether, from which the constant to be eliminated as the result contains differential coefficient in n. That is true, no? So here we have, earlier we have 2 arbitrary constant. To remove this 2 arbitrary constant, we have to differentiate 2 times. Right, and if we need to remove p, that is, if we consider as arbitrary constant, then we have to differentiate again, no, that means 3 times, it means third order. So if it is nth, you have n arbitrary constant, we have to differentiate n times to remove that constant, and original equations is there, then altogether n plus 1 equations we have. The most general solution of an ordinary differential equations of the order contains arbitrary constants. This will be probably seem obvious that from the converse theorem that in n arbitrary constants can be eliminated by differential equations of the order, but rigorous proof of offer much difficulty. Right, consider example. So there is another example we will consider. We will discuss how we can solve this example. Right, this is the example. here given d cube by over dx cube equals dy by dx, right? It is given that d cube by over dx cube equals dy by dx, right? So we are going to solve this one. So we can take assume that we are taking y equals a naught plus a1x plus a2 x to the power 2 divided by factorial 2 plus a3 x to the power 3 divided by factorial 3 plus a4 x to the power 4 divided by factorial 4 plus a5 x to the power 5 divided by factorial 5 plus an x to the power n divided by factorial n plus up to infinity, right? If we differentiate with respect to x, what happened? Here comes dy by dx equals a naught is the constant, then it's come as 0, then a1 x equals 1, then a2, then x squared we can differentiate, that is 2x factorial 2 plus a to a3, if we differentiate x cube, that is 3x squared factorial 3 plus a4 4x to the cube divided by factorial 4, right? If we differentiate this one, a5 is constant, then here this one 5x to the power 4 divided by factorial 5 plus this one an, if we differentiate this one, n to the power xn minus 1 divided by factorial n up to infinity. So dy by dx we can write a1 plus this one, you know that factorial means, if we can write a2 times 2x multiplied by 2 multiplied by 1, no, factorial 2, no, then this one we can write a3 3 times x squared, this we can write 3 multiplied by factorial 2, a4 plus 4x cube, this can you can write 4 multiplied by factorial 3 plus a5 5x to the power 4 divided by 5 multiplied by factorial 4, this you can write an n x to the power n minus 1 divided by n into n minus 1 factorial plus up to infinity. So you can cancel these coefficients, no? Finally you can take dy by dx equals a plus a2x plus a cube x squared over 2 squared plus a4 x cube over factorial 3 plus a5 x to the power 4 divided by factorial 4 up to an x to the power n minus 1 over factorial n minus 1 plus up to infinity, right? So here given, now we found dy by dx, it is given dy by dx equals to d cube by over dx cube, it means up to d cube by y over dx we need to find, dx cube we need to find, then we have to differentiate again with respect to x, right? Then here create d cube y over dx cube equals if we differentiate this one, that is 0, then we here a2 multiplied by 1 plus a3 2x over factorial 2 a4 3x squared over factorial 3 plus a5 4x cube over factorial 4 plus an n minus 1 x n minus 2 over factorial n minus 1 up to infinity. So here now as previous way we can write this is a2, if you write this one a3, no, 2 and 2 we can cancel, plus a4 as the previous way, 3 and 3 we can cancel, that is x to the power 2 over factorial 2. And here a5, here this also you can 4 and 4 cancel, then x to the power 3, here factorial 3, plus an n minus 1 and n minus 1 cancel, then x to the power n minus 2 over n minus 2 factorial, right? We need d here, sorry, here d squared y over dx squared. We can differentiate again with respect to x, then you can create d cube y over dx cube, right? So again a2 0 plus here a3x, no, 2 and 2 cancel, x is remaining, then a3 plus a4 times 2x divided by factorial 2 plus a5 times 3x squared divided by factorial 3 up to an times n minus 2 x n minus 3 over n minus 2, right? So then we can simplify again as previous way. Then here comes a3 plus a4 times x plus a5 times x squared over 2 squared plus an times x n minus 3 over n minus 3 factorial, likewise you can find, right? Then our given relation is d cube y over d cube equal dx. So here I am taking this equation dy by dx 1 and this equation 2 according to the given relation 1 equals 2, right? It is given. Our 1 is a1 plus a2x, this is our 1, no, a1 plus a2x, a3 a1x, sorry, a1, only a1, yes, a1 plus a2x plus a3 x squared over 2 factorial 2, yes, plus a4 x cube over factorial 3 plus a5 x4 factorial 4 plus an x n minus 1 over factorial n minus 1 equals, for third one, that is a3 plus a4x plus a5 x to the power 2 square root 3, then a6 x to the power 3 over square factorial 3 plus a to the power a7 x to the power 4 over factorial 4 up to an x to the power n minus 3 over factorial n minus 3 infinity. By comparing left and right hand sides, you can see that a1 equals a3, no, here you can see a1 equals a3, then a2 equals a4, no, a2 equals a4, then a1 equals a3, then a3 equals a5, a3 equals a5, no, a4 equals a6, a4 equals a6, then a5 equals this this a7, right? If we take a6, that is equals for a8, no, so you can see there is a relation, right? These are equals, right? It means you can see there are two types of equal coefficients. So hence we can write y equals a naught plus this a1s are all a1s are equal, no, then I am taking a1, then coefficients of a1s are first, if we take this y equals this one, no, if we take a1x, it means x is there, a1x plus then a1 equals to a3 means this one, then x cube over factorial 3, right, x cube over factorial 3 plus then a1 equals to a5 is there, x5 over factorial 5, x5 over factorial 5. Now you can see the pattern, right, it goes up to infinity, plus a2 times if we take a2 first, creating x squared over factorial 2, plus then a2 equals a4, then if we take a4, x4 over factorial 4, x4 over factorial 4, right. If we take, then you can see relation, pattern, x4 over factorial 4, right, x4 over factorial 4 plus x6 over factorial 6, likewise up to infinity you can take. Okay, and we keep this as third equation, and we will go to the, that is third equation, and we consider some hyperbolic functions. That is new for you, I think, right, hyperbolic functions. If we consider sin x, then hyperbolic function is sin x, sin then h, sin x, right. If we consider cos x, then hyperbolis is cos x, and tan x, then hyperbolis is tan x, right. Tan x equals sin x over cos x, right. Then sin x is defined as ex minus e to the power minus x over 2, and cos x defined as ex plus e to the power minus x over 2. But you know that e to the power x equals one plus x squared over factorial 2 plus x cube over factorial 3 up to infinity, and e to the power minus x, you know that is minus 1 minus x plus x squared over 2 squared minus x cube over 3 plus up to, yes. Then you here sin x is right, sin x is ex plus ex minus e to the power minus x over 2, ex minus e to the power minus x, that is I am taking half, I am find what is sin x, right. Ex minus e to the power minus x, if we subtract this, 1 and 1 cancel, x and x created, that is come as 2x, right. And these two subtracting, and this come as plus 2x cube over and plus 2x5 over factorial 5 likewise, and you can cancel these 2's, then it come as x plus s cube plus factorial 3 plus x5 factorial 5 up to infinity, right? So this you can see, you saw that relation in there, yeah, x plus x to the power 3 over factorial 3, x to the power 5 over factorial 5, like so. Instead of this one here you can write shin x, right? That is shin x. And how we go there, if we take cos x, it means ex plus e to the power minus x over 2, then half, I'm going to add these two, 1 plus 1 2, if we add this 2 that is cancelled, plus 2 times this one, no, x squared over factorial 2 plus 2 times x4 over factorial 4, likewise it is goes, then these 2's are cancelled, then it's come 1 plus x squared over 2 plus x4 over factorial 4 up to, you saw this relation in here, but 1 is not there here start at 1, but 1 is not there, so it means what is this, we can send 1 for other side, then it means cos x minus 1, so it means here what is it, cos x minus 1, because why, 1 is not there, right? So then we can write this relation, y equals a naught plus a1 shin x plus a2 cos x minus 1, where a naught, a1 and a2 are arbitrary constants, right? Those are arbitrary constants. That's how this is created, right? These are a1 a naught are a, then y equals a naught plus a1 shin x plus a2 cos x minus 1. This has a naught, a1 and a2 has 3 arbitrary constant. Similar reasoning applies for this equation and find those things.